Sometimes people ask me, hey Fred, are string hash codes unique? And instead of simply answering no, I reply with 3 additional questions. Question 1, what is the return type of hash code? That would be int. Question number 2, how many ints are there? That would be 4 billion, because an int has 32 bits and 2 to the power of 32 is about 4 billion. And question number 3, how many possible strings are there? So strings can get very large depending on how much memory you have. And in principle, the number of possible strings is basically infinite in Java. And so infinity is much bigger than 4 billion. And according to the pigeonhole principle, string hash codes cannot possibly be unique, right? Because you cannot fit an infinite number of pigeons into 4 billion pigeonholes. And if that sounds confusing, read the linked Wikipedia article. Okay, so what have I prepared for you today? So here we just have a simple Clojure wrapper around the native Java hashcode method, just so we don't have to deal with weird interop syntax later. I have a very simple example vector with the strings iPod in the hood, and then I map our hashcode function over that example vector. And here you can see the result. So iPod has the hashcode 3 million something, in has the hashcode 3,300 something, da has the hashcode 3,100 something, and hood has the same hashcode as iPod. That's interesting. So here we have a proof by example that string hashcodes cannot possibly be unique. Okay, but how often does this happen in practice? So for example, if we take a very large body of text, like a dictionary or the complete works of some author, will we find those hash collisions as well? So I have prepared 2 examples in text files. How would we process those text files? There is a nice function called withOpen, or a macro rather. And the syntax of withOpen is similar to the let macro, the let bindings. I can say I want to have a reader bound to the function location IO reader. That looks like this. And among other things, we can pass just a string for the path to the file. That would be home thread homes text. Okay, and then inside these parents we can work with the file, and then the file will get automatically closed. So this withOpen is similar to the try with resources in Java. Okay, now what do we want to do with the reader? We can say line-seq. That will give us a lazy sequence of all the lines inside the file. Right, what happens if we what happens if we execute that one? That looks rather weird. So here's the opening parent of the seq, and then apparently nothing else is printed. If we switch to the terminal, we can see that there's an exception. What's the cause of this exception? Here, stream closed. Okay, so this is a fundamental problem when you mix resources that have to be closed with laziness. Right, because again, here the file is closed and then the wrapper will try to print the sequence, and since the sequence is lazy, we can't read the lines from the file. That's a problem. Okay, let's rewrite the stuff to the thread write macro because I'm in love with it so much. And what we could do now is simply convert the lazy sequence into an eager vector. Oh, I forgot to close in parent. An eager vector. So this vec function will simply convert the sequence to a vector, and then we should see all the lines inside the file. There we go. Very nice. Now, how would we extract the words from a line? So for example, here I would like to have distinct strings, the adventures of Sherlock Holmes. I don't want a single string. I want these words to be contained in their own strings. So there's a nice function called regular expression sequence. We pass to it a regular expression that describes words, so that would be all big letters, all small letters, and as many as possible as the function will find. And then for an example string, let's turn back to this one. So for example, here's our example string. Let's put it over here and let's see if it works. Yeah, there we go. You can see all the words were successfully extracted from that one string. So let's turn this guy into a function. Let's call it word sequence for a given string. And then of course we have to replace this concrete example by the s, and I have to close a parent, right? Yeah, okay, and just if we're very paranoid, we immediately test this function. Do I still have it in the clipboard? Yeah, and it still works. Okay, very nice. So now we can map this word-seq function over our lines. Then what would happen? Okay, now you can see that the empty lines were mapped to the empty sequence, or the empty strings were matched to the empty sequence nil, and the non-empty lines were mapped to nested sequences containing those words. And of course, we don't want a sequence containing sequences. We want to flatten this nested structure, and this is so common in functional languages that we have a built-in function for that. It's called mapcat, and in other functional languages it's often called flat map. And that would look like this. That's really nice. Okay. You know what? Let's save this vector in a var, so we don't have to read it again and again from disk. So let's say words should be this. Okay, and then words should contain the exact same thing. Right, and now we don't have to read it again and again from disk. Okay, so now the next step is determining if multiple strings map to the same hash code. How would we do that? So there's a nice function called group by. We pass to it a function that would be the hashcode function, and then our collection, that would be words. And here we can see it. So for example, this large hashcode is only produced by the word combination. This smaller hashcode is produced by the word bad. And of course, in a real text like Sherlock Holmes, you will have duplicate words, right? And of course, those have the same hashcode. So let's replace the vec by a set, so we don't get duplicate words. Now you can see there's only one bad. Okay, so what exactly are we trying to find here? So if you replace the words with the previous example with only the false strings, here maybe this is a bit simpler to understand. We are looking for lists with more than one string, right? We already saw that both iPod and hood produced this 3 million something hash code, and these words aren't really interesting because they are very lonely in their vectors. Okay, right, so if we start like this and then say I only want to look at those vectors, those would be the if this is an entry in the map, then this is the key and this is the value, and I can say I'm only interested in the values, and you would write it like this. So this is the vals function returns a sequence of the map's values, and then you only get those vectors. And now we're interested in those vectors which have multiple elements inside of them. So that would be filter, and that function doesn't exist yet. So how would we like to call it? Contains several ? And of course we have to write that function. So let's say contains several of some collection basically that the count of the collection is at least 2, right? Okay, and here you can see for our very small example, we found exactly what we were looking for. Now let's do that with Sherlock Holmes. That would be these words. And now here you can see the empty sequence. So how big is this Sherlock Holmes words vector or set now? Okay, it's only 8,000 words. So inside those 8,411 words, there's not a single hash collision as demonstrated by this empty sequence. Okay, that's rather disappointing. It's not disappointing if you think, well, I don't really want to have these collisions, but for the purposes of this video, it would have been much more interesting to find collisions. So, of course, I did some research and I used a different text file. I used a German dictionary. Okay, and if we do it with that German dictionary, I forgot to execute everything, you can see some examples of collisions, but these don't really seem to be valid German words. So if you're German, you would expect this word to continue with an umlaut. And of course, we forgot to put umlaute in our regular expression. So SZ. Let's see if that gives us something better. And it does not, because that was also not very easy to find out. The encoding of that particular German dictionary file is not UTF-8, but Latin 1. And the technical term for Latin 1 is ISO 88591. And then we should get more sensible words. Yeah, that's looking good. And indeed, we have so many collisions that we don't see them all in the same line. There are too many, so let's print them all one by one to the terminal. There we go. And now we can go hunting for funny hash collisions. Let's see, what are my favorites? I had 3 favorites. Yeah, that's my first favorite. You can put this into Google Translate for your own language. Then we had this one is rather funny, and this one, I also like this one, it's really cool. Okay, and here you can see 2 interesting examples. If you can figure out why these examples collide, then it's trivial to generate an infinite number of strings that all have the same hashcode, basically. Or let's say an infinite number of pairs that have the same hashcode each. Right, so if you know how hashcode is implemented, this should be easy, an easy exercise. Okay, so maybe a quick recap. What did we do? We wrote a Clojure wrapper around the native hashcode function just to make the following code a little nicer to understand. Then we had an example vector with 2 words that had the same hashcode, as demonstrated here. Then we wrote a function that extracted all words from a string. Right. Then what did we do next? We read in the entire or all the Sherlock Holmes novels, basically. All the lines in that file, then all the words in those lines, and then flattened so we don't have a nested structure. And to remove the duplicate words like bad, 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 we stuffed them into a set because sets don't have duplicates. Okay, and later we changed that to a German dictionary with a different encoding and changed the regular expression to contain umlaute. Okay, then we defined a function that determines if a collection has multiple entries. We don't really need that guy anymore. And then we said, let's group the words by the hash code. Let's only look at the values of the map entries, so we only see the colliding strings. We're only interested in the vectors with multiple strings that collide, and then we printed those to the terminal. Right. And by the way, this function can be implemented much more simply. So instead of saying contains several, we could simply have said next, and we would have seen the exact same output. That's why is that? So here's the documentation of next. Where can we see that's the next function, right in the lower left corner? And if you say next for a vector with just a single element, doesn't matter if it's a number or something else, you get nil. Nil is the empty sequence, but it's also falsy in Clojure. So the filter function will thus ignore vectors with only a single entry. And if you have vectors with at least 2 entries, then the next function will give you the remaining sequence, and that won't be nil if there's at least 2 elements inside. Right, but of course this is terribly unreadable code, right? Don't do it like this. I would say we could, if we wanted to, replace this guy with next call. That should still work. Let's evaluate this function and this guy over here. Yeah, still works. And you can get rid of the def now, replace it with a simple def and say contains several is nothing but an alias for the next function. But again, is that really readable? I don't know. I think it's an interesting trick, but I wouldn't really do this in practice unless you know that all your audience is very experienced Clojure programmers. But why would they watch my videos? Okay, so your homework is really simple this time. Find a dictionary of your own native language, see if you can find funny or interesting hash collisions, and then post them in the comment section below, and also translate them to English so other viewers will be able to take part in the fun. Bye!